For integration, the SAT is on chapters 4 and 5. However, the way chapter 4 approaches integration in terms of learning it, I think is slightly bonkers. So we will do chapter 4, but we're going to do for B, E, F, and then go back and do D, A, C, G. In that order. Trust me, it's just better this way. I'm not a big fan of the order the book does it. We'll do it this way. Before diving into the mechanics of integration, there is, I guess, almost a bit of maths philosophy I'd like to start you thinking about that we may not have thought about before. If you're considering polynomials, you guys will have seen this instruction before. And you know that if we're talking polynomials, I can give you anything here, polynomial-wise, like a pair of brackets, whatever, 3 brackets. It might be a bit of a slog, but you'll be able to do that and get an answer. And what you might have found, and then you'll put, and so you'll expand it out and you'll get a polynomial written in traditional form. Like if you expand and simplify this, you'll get that. 3, 4 brackets, fractions in here. No matter what, you could expand and simplify. What you might not have thought about before is the fact that I can give you infinite different things here. You would think down here, like this can be anything. You would think when it moves down here, this is a set that covers everything. But there are some things here, x squared plus 1, for example, that you can't factorize back. So in this anything list, there is nothing that will get you to here. So there's some things that you can expand and simplify and then factorize and jump between the two, and there are some things that just can't be expanded and simplified and can't be factorized. This you can't go back to. Does that sort of make sense? So there's a certain class of things that can't be factorized. The reason I'm talking about that is that there's a similar relationship. You guys so far have looked at differentiating. Taking a y or an f of x, differentiating it, you get dy dx or f dash x, depending on the notation you're working with. There is a process that we'll learn today called anti-differentiating, which is going back. Everything you see can be differentiated. So using those 4 rules, product, chain, quotient, etc., using those rules, you can differentiate absolutely everything. That's the equivalent of expanding and simplifying. Slightly frustratingly though, not everything can be anti-differentiated. There are functions out there that you can't anti-differentiate, and there aren't the same simple set of rules for anti-differentiation. Methods as a course only scratches the surface of integration, or anti-differentiation. We only look at relatively simple examples. Also, anti-differentiate is basically the same word as integrate. Integrate is the word that we'll use going forward. Technically, to anti-differentiate is to do something on an expression. Integrate is, I think, to do it on an equation. It's probably better, let's go again. Alright. Finding antiderivative of x. So, what this is saying is that we have a function, f dash, and it's x. The question is, where could this have come from? So, we're basically doing integration by observation. You're observing that something has been differentiated to give you x. Where has the x come from? So, x will have come from an x squared, because you know when you differentiate, you drop the power. So, it's come from an x squared. The problem is, you know when you differentiate the x squared, the 2 comes out the front, and there's not a 2 here. So there must have been, yeah, well done, a half. A half x squared will give you an x. We would say this is the antiderivative of x, meaning that if you did differentiate it, you'd get back to this. Therefore, if you integrate, it goes the other way. So the antiderivative of x is a half x squared. And this is a bit trippy because you've spent so long training your mind to go the other way, you're now having to go backwards. Where will an x squared have come from? Good, x squared must have come from an x cubed. If you were to differentiate x cubed, it would throw a 3 out the front here. So what do we do to combat a 3? Yeah, a third. So, the antiderivative of x squared is a third x cubed. What about x to the minus 4? Where will x to the minus 4 have come from? Good, it will have come from an x to the minus 3. And then what fraction will go out the front to make sure that it goes back to a positive 1? Good, negative a third. You need the negative in there to cancel out the negative from that. You need the third to cancel the 3 to get you there. So the antiderivative of x to the minus 4 is minus a third x to the minus 3. It's doing the rules you know, but backwards. Alright? X to what is it? A third? This will get slightly nasty. X to a third will have come from x to the 4 thirds. And to cancel the 4 thirds coming down the front, you need 3 quarters. 4 thirds times 3 quarters is 1, so it's that. Now I'm afraid the meme printed on the wrong page for you guys, but that's meant to be here. Alright, integration. There's something we probably haven't thought of. Remember here how I said x will have come from a half x squared? What if the original function was a half x squared plus 3? That would still differentiate to x because the 3 differentiates to 0. So a half x squared plus 3 gets me x. So if you're told you've got the function x, please integrate it, the function it came from could have been a half x squared plus 3. It could have been a half x squared plus 7 or 17. The constant there doesn't really matter, but it could easily be any constant because it will differentiate out to nothing. And here comes the most annoying way to lose a mark. If you are going to integrate something, that capital F of x is its antiderivative. The integral of f of x is its antiderivative plus c, to reflect that we don't know where the c would have been in the original function. If you don't write the plus c, it is a really frustrating way to lose a mark. And there's a good set of memes on the internet if you want to look up what happens if you've missed the plus c. The way this reads is the antiderivative, or the integral of x squared dx. So it's asking, if a function was differentiated and you got x squared, what would that function be? That function would be a third x cubed plus c. Because if you were to differentiate this, it will get you back to there. And so there are many applications of this which we'll look at in future lessons. Today is more learning about what gets you back to the starting point. This is a formula that some of you might find useful. Actually, you will find useful. Basically, it's saying the integral of k f of x is equal to the k times the integral f of x. I'll give you an example of that. If you're looking to integrate 5x to the power of 3 dx, that is going to be 5 times 1 on 4 x to the power of 4 plus c. So that x to the power of 3 has come from 1/4 x to the 4, which is 5 on 4 x to the 4 plus c. The other way to think about it is this constant of 5, if it's a factor, can be removed out the front of the integral. The integral and the dx almost treated like a pair of brackets. You can think of this as 5 lots of the integral of x to the power of 3 dx, which is 5 lots of 1 on 4 x to the 4 plus c, which is 5 on 4 x to the 4 plus c. Slight technicality that's probably worth noting is that this actually belongs in brackets, because you've integrated that with a 5 at the front. It's 5 times the result of this function. So many people will be tempted to write a 5c there, because that 5 feels like it should go into both. But if c represents an arbitrary constant, just like any constant number, 5c is equally arbitrary. We just leave it as c, which is an annoying and slightly weird convention because you're expecting the 5 to go in both, but if c is any number, and it's just there to represent a constant, 5c isn't any more meaningful or significant, so by tradition we don't write 5c, we just leave it like that. The second rule is neat, and very much related to one of the rules of differentiation. So you know that if, say, if you have 3x squared plus 2x, if you were to differentiate that, you would attack each separately because you differentiate each part, each term with a plus separately. Similarly here, if we were to integrate this, this would be equal to the integral of 3x squared dx plus the integral of 2x dx. And if we want to go further, we could put the constant out the front of each. Whether you want to put the constant out the front of each to make your life easier is probably up to you. But what would the integral of 3x squared be?
X to the 3.
Good, x to the 3. And the cool thing is, when you differentiate it, going back to here, the 3 comes out already. You don't need a fixing number out the front. That's exactly it. Here is the other bit of convention. 2x comes from an x squared plus c. Now, according to our rule, we're throwing out the c's. Really, this integral here should throw a c, and this integral here throws a plus c. Each time we do an integral, we get a plus c. A bit like the logic over here, if c is an arbitrary thing, we're not going to do 5 lots of it. In this case here, if this is throwing a c and this is throwing a c, we wouldn't write plus c and plus c. We just do it once on the end, because it's arbitrary. So there is a bit of sort of convention around this, because it would be pretty tempting to say, okay, that according to our first rule is x cubed plus c, this is x squared plus c, therefore the answer is x cubed plus x squared plus 2c. And that feels like it should be, but it's not the case. You only just do one c to add it all up. Alright, our first set of integral rules, and we'll have some practice on them. A constant integrated comes from kx plus c, which sort of makes sense because if you differentiate this, kx differentiates to k, c differentiates to nothing, and that will differentiate to that. This is the one that we've been using so far. It looks scary, but it's essentially that. E to the x integrates to e to the x plus c, simply because if you differentiate this, it gets back there. Where we start getting more interesting is you're starting to see our derivative laws in reverse. So cos doesn't come from, well, cos comes from sine, because if you take sine and differentiate it, you get cos. Sine doesn't come from cos, sine comes from a negative cos. Because if you differentiate cos, it throws negative sine, so if you differentiate negative cos, it throws positive sine. So for those of you who have remembered when differentiating cos, it changes sign, slightly frustratingly here, when integrating, the reverse is true. But hopefully you can sort of see the logic to that. And now we'll do some practice. So, give me a second to get everything board.
When you wrote the expression with dx in the end, is that the equivalent of dy dx for integration?
Yes, it means you're going with respect to the x-axis. And for, it's just been videoing, not me, the last 5 minutes. For methods, we'll only go with respect to the x-axis. But for your investigation, some of you might have a play with going integral with respect to y.
Okay.
But that's beyond the course. So yeah, for our purposes, you'll only see a dx. Alright, the integral of x cubed minus 2x squared plus 5 dx. Now, if you were asked to integrate this, you would be encouraged to, well, you'd be allowed to split the integral across every sign. So you wouldn't necessarily write this line. You guys will get fast enough to where you're not needing to write this line. But this would be the integral of x cubed minus 2 lots of the integral of x squared. Each of these is dx, plus the integral of 5 dx. So, I've removed the minus 2 out the front of the integral and written it like this. Again, in working out, you wouldn't have to write this line, but it helps us approach it nice and easily. What would the integral of x cubed be? Where does that come from? Good, it's come from x to the 4, and you need a fourth out the front to sort of counteract that fourth coming down. Where has x squared come from? Good, it's come from x to the 3, and there will have been a third to counteract it. Bear in mind, there's still this minus 2 at the front, which is going to give us a minus 2/3 x cubed. And what's the integral of 5? Good, 5x. And yes, plus c, either here or in the next line. Honestly, if you've got more tidying to do, we only really care about the c at the end, but it is worth reminding yourself, sure, with a plus c. So this would be 1/4 x to the power of 4 minus 2/3 x to the 3 plus 5x plus c. Alright. Integral of, I won't rewrite the question, but if you were going to write this as a more convenient way to work with, how would you re-express that or change the expression slightly?
X to the power of negative 3.
Good. X to the negative 3.
Say x to the power of 5.
Apologies. Dx. Alright. I won't write it as separate integral signs, we'll just do each one separately. Where does x to the minus 3 come from?
Negative 1 over 2 times x.
Nice. Because when you differentiate this, this power will drop by 1 to get negative 3. When that power minus 2 comes out the front, it needs a minus half to welcome it to get us back to a positive 1. What about this one here? Well, that will have come from an x to the 3 on 2. And then you're looking for 3 on 2 times something gets us to minus 1. The answer is minus 2/3. It's lots of playing with fractions. The good news is you can always differentiate and make sure you end up back there. So the check on your answers here is to differentiate and end back at the start. Alright, one more. Alright, where does the sine x come from? Negative cos. So this will have come from a minus 2 cos x. And you can always check you're on the right track by pretending to differentiate this. If you differentiate cos, you get minus sine. You have minus 2 lots of minus sine, gives you positive 2 sine x. So you know you're on the right track. Where will the cos come from? Well, cos will come from sine, so this becomes that with a plus c. Alright, a step harder. Cast your mind back to when you first learned to differentiate. It was late last year, and often you would have to break things down to easy looking chunks because you hadn't yet learned the power rule and the quotient rule, etc. Here, for integration, you're not going to learn the power rule. Integrate rule is not an equivalent rule. Instead, we have to break it down into easy to attack chunks, like this first one is here. So, our approach here is to expand and simplify and get it chunkable. If that makes sense. So, I would rewrite this as 3x plus 2 on x, 3x plus 2 on x dx. And then we're doing expanding and simplifying in here until we can get to something where we can just pick each one out. So this is the integral of 9x squared plus 3x times 2 on x, which is 6, times 2, which is 12, plus 4 on x squared dx. So I've done the middle two terms as the shortcut, but you can completely use FOIL and then collect like terms and you'll end up here. Now it's attackable. And note that when I actually want to write the answer, I'll drop the integral sign. So then when we're integrating, this is going to go. That will have come from an x cubed. I want to end up with a 9, so what number goes there? 3. Sweet. You can follow the green box rule if you want, but honestly, lots of you will just find yourself thinking about, okay, where I need to end up, so what do I need there? Alright, what would I need to end up with a 12? Beautiful. This is really, I'll write it on the side, that's really 4x to the minus 2. It will have come from an x to the minus 1, and because I want a 4 there, what do I need to put here?
Minus 4.
Good, minus 4. Minus 4. And then the favourite thing to get, plus e. Alright, last example. How would you think about chunking it? Pardon?
X to the negative half times 5.
Yeah, nice. You're going to effectively multiply each of these to with an x to the negative half. So this will become 2 minus a half is x to the 3 on 2 minus 2x to the minus a half dx. So you're distributing the denominator into both of the tops. And now it's into sort of a chunk form. We can work on each chunk. This x to the 3 on 2, what will that have come from? Good fractions, Jim.
2 and 5, x to the 5 and 2.
Good. So it will have come from that as a power. For some reason I always did the power first, and then you write 2 and 5. Because they will multiply to make 1. This will have come from, minus a half will have come from positive a half. Positive a half times what gets us to minus 2?
Minus 4.
Yeah, minus 4. Nice. Plus c. So to get the idea, it's a bit trippy going backwards. Now here's the most frustrating thing. I haven't taught you how to do every single question out of 5B, but these are the ones I'd really like you to have a shot at today. 5B question 1 and 2, don't do them all, do odds. I have a sneaking suspicion it's meant to say 4. 4. Then 4E, 1 to 7. And I will go upstairs and get your sets, and then